Okay, let's think about this manual clock situation. Now look, supposing I said to you, all right, we know about switches. We know how to get ones and zeros from switches. Okay, so supposing I said to you, look, here is a switch, okay? And we could look at this, for example, as a normally closed switch. So maybe its condition looks like that, okay? And when you press the button, or I have 5 volts sitting here, and when you press the button, then what happens, okay? Maybe the switch now basically goes to a position like that. You've opened it up, so what happens to this voltage here? As soon as we open this up, basically this voltage, this is where we're taking our signal right here, this voltage is going to do what? It's going to rise up, okay, when the switch is open. Go back to 0 when the switch is closed. So here we are, as it were, pressing the switch here. We've opened up the terminals, and basically this has gone up, okay, to 5 volts. And then what happens? Okay, well, when we take our finger off the button, remember we're looking at this voltage here, when we take our finger off the button here, what's going to happen next? Okay, well, basically the terminal or the connector of the switch then goes back and makes contact like so. All right, you might say, well, yeah, this has gone up and it's come down back to 0 again, like so. All right, but the problem is that when this little bar mechanism, this guy here, it hits this terminal, it bounces up again. It's a mechanical problem. It actually bounces up again, and it becomes like this again momentarily, and it becomes an open. And so what we see is this voltage actually rises up again, and then goes back down again, hits, and then bounces open again. So as it goes back, as it makes contact, it goes down, bounces, and it creates this rising edge. And so what we end up with, as this guy is bouncing before it actually settles to a closed condition like this, remember we only pressed the button once, took our finger off the button, it came down, it hit the contact, bounced up, backwards and forwards, and creates multiple edges. Now these edges, right, the time period is very fast, but remember, if this were an output that is going to a clock input on a flip-flop, every time you get an edge, every time you get a leading edge, you're going to change states. And so really, because of this bouncing problem, creating these multiple edges, this is a real problem in attaching this kind of a signal really to the clock inputs on the flip-flops. It wasn't a problem for the crossing switch because that didn't go to a clock input on a flip-flop. But if this were the kind of configuration that you wanted to use to provide your clock, it's not going to work because of this bouncing problem and the creating of the multiple edges. So it's a real consideration. We have to solve that type of problem. Okay, so this is a circuit that could be used to really solve that problem. Okay, this is a special kind of switch here, very common of course. It's a single pole double throw switch. Okay, so we're going to imagine the switch is not pressed, and basically the switch connection is going to sit like this. We haven't pressed the switch at this point. When we press the switch, this connection would be from this point to this point. Okay, that's when we press it. When we release it, it goes from this point back down to here. Okay. All right, so again, single pole double throw switch, very common switches. All right, now what we have here are 2 Nand gates, okay? Now these gates, let's look at the configuration of them. The output of this gate, which I'm calling clock, which will be our clock, okay? The output is also fed to the input of this Nand gate here. The output of this Nand gate is fed back to the input of this Nand gate. And then over here, the other input of the Nand gate basically connects to the contact of the switch, also to maybe a 1K resistor connected to 5 volts. And then similarly over here, this other input is connected to the other contact of the switch. Also, we have maybe a 1K resistor here, also attached to 5 volts. Okay, so what we're going to do is we're going to look at the state of this circuit right now with this particular connection. Now, it's always a useful idea, I think, when you're thinking of this sort of thing, is draw the truth table down for the NAND gate, because we're having to figure out what's going on with these NAND gates, and so I'll just do that. Look, for want of, I guess, better labels here, I'm just going to say we've got A, B, and Y. In other words, I'm just writing a truth table down for a NAND gate where that's A, that's B, and that's Y. Okay, that's all I'm really doing. So we've got 0, 0. The output would be what? Would be a 1. Okay, we've got 0, 1. The output would be what? A 1. We've got 1, 0. The output would be a 1. And then finally we've got 1, 1. Okay, the output would be a 0. So it's important just to write that down to help us in our thinking. Okay. All right, let's have a look at what's going on here then. All right. Well, look, this input over here, what's happened to it? It's directly connected to ground, isn't it? A direct connection to ground. So really, we must have what? Logically, we must have a 0 sitting there, mustn't we? A 0 sitting there. Okay. This input's not actually connected to anything. Okay. So very little current going here, and so therefore, basically, this voltage level here is going to pull up to 5, and so what we see sitting here is a logic level 1. Okay. Now let's look at the NAND gate sitting here. We've got one input being a 0. Well, if any one of the inputs is 0, the output's going to be what? The output's going to be really sitting at a 1 over here. Well, that 1 is then fed back to the input of this NAND gate. So we've got a 1 sitting there on that NAND gate. Okay, so a 1 and a 1 fed into a NAND gate, 1 and a 1 fed into a NAND gate. This output over here is sitting at 0. And so that's our, if you like, our condition of the circuit when the switch is connected like so. You haven't pressed the switch at this point. The clock output is sitting at a 0. Okay? Okay, that was the case we had before. Remember, our switch was connected really in this position like so, okay? That established this point of being a 0, and we had these outputs as I showed you in the previous slide. Now, we're going to press the button. As we press the button, what is going on? Okay, this contact moves from this point here, moves all the way across, and contacts like so. All right, so that's our first contact. Now, I'm not saying when we press the button that this doesn't come across and hit and bounce off. It will do. But let's first of all consider it's actually made contact. We'll worry about the bouncing in a moment. Okay, so there's our first contact situation. What's going to change in this circuit? What do we see actually changing here? Well, we do see the 0, right? This is no longer a 0. This 0 is going to become what? A 1, isn't it? Okay. What's going to happen over here? This 1's no longer a 0, no longer a 1 because of this connection. This 1 is in fact going to go to what? It's going to go to a 0, isn't it? Okay, so now if we have a 0 at one of the inputs, a 0 at one of the inputs, this output over here, it must what? It must go to a 1. Okay, now have a look at this now. This is fed back here, so I now have a 1 sitting here. So I have a 1 and a 1 sitting here now, okay, which does what to this? A 1 and a 1 here really causes this output to actually go to a 0. And the 0 is fed back over to here like so. So this is our new condition now, isn't it? Where this is now a 1, okay, this is now a 0, okay, of course this has gone to a 1 here, this has gone to a 0 over here due to really that connection. So that's our new condition. All right, so we've got a clock, which is great. We've got a clock. Now we'll consider the bounce action. Okay, so here once again is that pressing the button. Okay, this connection is made like so, all right, and so the clock has, and this is what we're calling the clock over here, the clock has become a 1. So we're seeing that clock sitting at a 1 now, okay? These are the conditions that reflect that, all right? This guy has gone up to a 1 because there's no connection here. Now consider what happens. By the way, that's a little, of course, that's our NAND gate truth table. Now consider what happens. This comes across as you press it, hits contact, and then bounces away. So I'll show you that bounce condition. It's moved away like this. And it's going to go backwards and forwards, okay, until it settles down, having made that contact. And when you release your finger off the button, of course, this will go back the other way. But let's look at that bounce. It's bounced open. If this guy has bounced open, what's it going to do to this logic level right here? Remember, if I've got a direct connection to ground, that is logic 0. But if it's bounced open, okay, what's going to happen? There is no connection. This stage, there's no connection to what? No connection to ground, yes. Okay, so what's going to happen to this logic level? This logic level is going to go to a 1. Be it for a short period of time, because this is actually bouncing, but be it for a short period of time, that went to a 1. Okay, now what's that going to do to the output over here? Well, let's think about that a second. If this goes to a 1, what is the input to this NAND gate now? It is now a 1 and a 0. Well, let's have a look at that. A 1 and a 0. The output's still a 1. So the output has not changed, even though this one input has, due to the bouncing action, this output over here has not changed. All right, then this closes up again. So you might look at that now going back to 0. Now I've got 0, 0 as inputs to this NAND gate. Well, 0, 0 is still an output of a 1. And then as it opens up again, okay, this goes back now to a 1 because we've now got another open due to this bouncing action. Well, I've now got a 1, 0, which a 1, 0 is still a 1 at this output over here. And so really what this has produced, as I pressed the switch, I produced a nice stable clock with one edge for one press. Okay, and then when I take my finger off the button, this would go back down to 0 and would not be a problem. Similar reasoning could be applied with the bouncing on this side over here. So then this then becomes a circuit that you can use, okay, to provide a manual clock, so you can really single step, as it were, through your states. So move into a state, check it out, press the button, move into the next state, check it out, and so on. So what have you got? You've got basically two NAND gates configured like I'm showing you here. You've got these inputs connected to through a resistor to 5 volts on either side. And remember, this is your switch over here, single pole double throw switch. Now your only challenge is to find out where the common, as it were, terminal on the switch is. And you can do that with a DVM. All right, now look, that's going to basically end this particular video. Next time we're going to look at what some of the problems are with this traffic light system. One of the problems, I think, is that crossing switch. You're going to keep it pressed basically until you actually change states. If you just kind of tap it momentarily, well, it may or may not change states. The other issue is that basically the machine so far only allows one state time for the people to cross the road. Think about that. That's not a good situation. And look, what I'd like you to do is think about maybe how you could modify this system really to allow people more time to cross the road. Could it be adding more states? Think about that. Next time we'll talk about maybe some kind of timeout feature that we could also use to allow enough time to really cross the road.